Hi, this is David Woolworth with UCR Supplemental Instruction, here again to talk to you about Physics 40B, and this time we'll be talking about heat engines and refrigerators. So this is the culmination of all the thermodynamics work that you've done so far, so it makes sense that this is sort of the last section of the class. And it's also the most complicated, I guess you could say. It's going to deal with all the things we've seen in previous chapters, leading up from ideal gas problems up to processes, and then the laws of thermodynamics with work and energy and heat and all those sorts of things. So we're now finally putting them all together. And this is also cool because this is the part that most directly applies to real life. We're actually going to be talking about things that, even though they might be put in conceptual terms, relate pretty closely to the things that we see in our everyday. Refrigerators in the title here, that would be one of them. Most of you probably have one of those. Heat engines, that's a pretty generic term, but it refers to something like a car engine, which is probably just as ubiquitous as a refrigerator. So now we're going to be talking about these things in practical terms as well. And so I want to kind of connect the bridge because I know the textbook likes going over these things in conceptual terms. So first off, though, let's just start talking about heat engines. Now, this is probably a diagram you've seen before. You have a hot reservoir and a cold reservoir. And what that means, a reservoir in this case, is just an abundance of thermal or energy, or like a receptacle for energy, where you can move something to one side and not really affect it, right? So this is like, say, like an ocean, the cold reservoir. And if we put a couple drops of water in there from a hot reservoir, it's not going to change the ocean. The magnitude is just so different. So these are conceptual terms, right? When we talk about heat engines, what we mean then is that we're taking some thermal energy from the hot reservoir and moving it to the cold reservoir. This makes sense, right? If you had something hot next to something cold, naturally thermal energy will transfer from the hot object to the cold object. And so in much the same way that's happening here. Now, we don't need to do anything to get this to happen, but we can get work out of it. And so that's the purpose of, say, a car engine. So I'll just label this work. All right, so that's still really conceptual. What does that actually mean? What is the hot reservoir in a car? What is the abundance of thermal energy? Well, it's a little trickier than in a in a refrigerator, because in this case, that energy is actually what's in your fuel. So gasoline has what's called a heating value, for assuming a gasoline car. So a heating value of gasoline, and it's about, I think 45, somewhere in the 40s megajoules per kilogram. So what that means is if you were to combust 1 kilogram or 1 liter, approximately the same thing, of gasoline, you would get 45 megajoules going from the hot reservoir to the cold reservoir. So the hot reservoir is just the chemical energy in the gasoline. What is the cold reservoir? So what's the cold thing around your car? Nothing really, unless you have a fridge in your car, but in this case, it's relative, right? Cold is a lot of things compared to combusting gasoline. So in this case, it would be the entire atmosphere. But of course, we, in practice, don't just allow energy to move from the hot reservoir to the cold reservoir. We're using some of that for work. And that cycle is shown here in the Otto cycle. This is a pretty basic cycle for a car engine. And what this does is it shows that in these two adiabatic processes, work is being done. Under this one, this is where your compression is done. So we're using the engine's power to compress the gas, and therefore we're using power, and we're adding energy into the gasoline, or the gas inside of the cylinder, rather. And then at this top adiabatic process, this is where the combustion occurs, and that's where we get more energy back out. So we have a net work done by the gas in this case, and the area inside the cycle is what we get out of it. So that's pretty simple, right? Let's move on to talking about refrigerators. So refrigerators sort of have the opposite purpose, right? We have something that we want to remove heat energy from, and that thing might not necessarily be an abundant source of heat like a hot reservoir. So if we put food in our refrigerator, our food isn't necessarily hot, but we do want it to be colder, whatever temperature our refrigerator is set to. And so in this case, instead of taking energy from what we're calling a hot reservoir to a cold reservoir, we're doing the opposite. So the cold reservoir is the inside of our refrigerator. We keep it at that temperature, and we're trying to, even though it's still colder than our outside environment, remove more thermal energy from that interior of our refrigerator. So this is going against the natural flow of heat, right? Normally we have something naturally flowing from something hot to cold, but now we're doing the opposite. And where we got work out of the process going the opposite direction, if we want to move energy from the cold to the hot, we need to put energy in. So we're doing the opposite here. And this work is now being done by us, and it's being put into the system. So this is in almost every way the opposite of a heat engine. And the cycle that goes along with it, the most common one, which we'll see, is called a vapor compression cycle. This isn't the only one. We'll probably talk more about Brayton cycles in this class. If you're a mechanical engineer like me, then you'll definitely get to know this. But as you can see, even the direction in this cycle doesn't look too different from the Otto cycles we saw before. But you'll notice that the direction is different. So in this case, what we want out of it is energy from the cold reservoir into the hot reservoir. And some of the energy in by work will be doing the same thing. But essentially, it's very similar. It just has the opposite goal, really. And so that idea of a goal sort of brings us to the topic of efficiency. So efficiency, which is also one of the core components of this chapter, is just how effective of a heat engine or refrigerator is this cycle. So just a brief rundown, efficiency in its most general terms is usually equal to, in this case we'll say, I'll draw out a fraction here, the amount of energy you put in versus how much of what you wanted to go, how much of that energy went where you wanted it to go. So you can say energy in, that's sort of like what we paid. I just mean energy that is available to us that we put into the cycle to make it work. And then the top would be how much got where we wanted. So what's a good term for this? So however much energy we got out of that, which is pretty crude terms, but hopefully you understand what I mean. So if we write this as QC, the energy that we were able to remove from the cold reservoir, is QH, the amount of energy that goes into the hot reservoir, and we'll just leave work for the amount of energy we're putting into the system. What do we want out of the system? Well, we're not trying to heat up the area around us, so QH isn't what we're looking for. What we want to do is cool down the inside of the refrigerator. So QC in this case would be what we want. So we'll sort of extrapolate that here. Right, so if QC is what we wanted to happen, right, we want to be pulling energy out, we can put that in the top, that's what we wanted to happen. And then in the bottom, well, what did we pay? Well, QH is the combination of the amount of work going in and the heat moving from the cold reservoir. But in this case, what we're paying in this case, like what came out of your wall in this case, right? Your energy, or the energy comes from electrical power grid. So that is work, right? That's how much energy we're putting into this refrigerator to make it work. So this is what we paid. So this would be an efficiency for a refrigerator. If you wanted to go back and do the same thing for a heat engine, well, what do we pay? In that case, it would be the energy coming out of the hot reservoir, and what we want out of it is work done. So as we saw, we know how much energy can escape combusting gasoline, but only some of that is going to come to work. The whole thing. So again, that's for a heat engine. It's not the only ways you can write this, as you'll see there are several manipulations, but this would be the basics behind it. Right, so that sort of clears up what exactly this diagram means. I know they like throwing this at you and how you can connect it to the cycles, which you'll see in PV diagrams. And also I hope it connects us to the real world stuff, because this is as close as this class gets. So I hope you learned something, and we'll see you next time.